I'm Aggregations, I'm the CTO at DTrace. I'm also one of the original 3 authors of DTrace, along with Brian Angel and Mike Shapiro. So, folks who hear the performance talk where I talk about DTrace, did you see that? Okay, good. Just one. Because I'm going to recap a lot of that. And folks who have heard of DTrace before, and people who have used DTrace before. Okay. My hope is that this night we're going to get a couple different perspectives. I'm going to start with a brief history of DTrace, where it came from, some of the motivation behind it, where you can find it, and we're going to see some uses of DTrace and on different platforms, and use cases, and so forth. Please jump into questions for all the speakers. They'd love to feature all of it. So I'm going to start with where DTrace started from. Does anyone recognize this box? And it's not a data, so don't anyone feel free to shout it out if you know what it is. All right. So Sunny take geez, I'm really dating myself by knowing any box particularly by Sunny. This is kind of the genesis of DTrace. This box was made my college Brian and Mike at the time were working very hard to get the world's best performance numbers out of this thing. And they were to do it, they were turning to all these existing tools. They would run NP-stat and then the DNA stat and PR stat and log stat and IO stat. All of these different tools would give you a very narrow window into just one part of the system, and then kind of stitching it all together. Figuring out how to make sense of this mountain of data without it really naturally being real data. So all these different tools gave very, very narrow glimpses into what they needed. And they were able to eventually solve this problem. But it was really the acute problem of how to do systemic performance analysis, and in particular how to do systemic performance analysis of production systems. Everyone's experiencing that already. Any better? So we need one tool that can bridge all these different components. So DTrace is that one tool. Let me talk a little bit about the motivation for DTrace. So DTrace is systemic in scope. You can look at low-level operating system facilities like CPUs and disk I/O and networking and things like that, all the way up through the kernel and through the libraries up to your application, whether it's in C, Java, Ruby, PHP, Perl. So it's taking truly a systemic view of everything that's going on a system. It is safe to use in production. That was one of the most important aspects and design principles for DTrace. We have to make sure that when you're hitting a problem on your most expensive problem on your most expensive system, that DTrace is available and it's safe to use. It won't cause an outage, it won't cause data corruption. So systemic scope, safe to use. So we started this in, and I'm going to linger on this next slide for about a second. We started this in about 2001 3. In 2005, we were the first open source contribution from what was then Solaris and became Open Solaris. And DTrace shipped first as part of Solaris 10 in 2004. DTrace is award-winning. In 2006, we were honored by the Wall Street Journal with their top honors in their innovation award. I highlight this, and now if you'll permit an aside, the things that we beat out were some solar energy panels thing and something about inhalable insulin. And this was one of the highlights of my career. Just finally, I could talk to my parents and tell them what I did by saying it was better than inhalable insulin. This led to some strange confusions. Brendan Gray, who you're going to hear from later, was a colleague of mine at Sun and Oracle, worked together very closely at a group called Fishwhisper, with a lot of work with DTrace. Brendan had been using DTrace long before that, probably the world's greatest DTrace power user. When he heard the phrase, Brendan's from Australia, when he heard the phrase, DTrace is better than inhalable insulin, he thought this was some American phrase. Like it was something that people say, like he would say, throw some shrimp on the barbie or something. So it was only 2 years ago that he found out that he was really better than inhalable insulin. And I don't know what he was saying to Americans, saying, oh, this is better than inhalable insulin. So where do you find DTrace today? DTrace started off in Solaris, and open source, and it's since been ported to these different platforms first to macOS 10 very surreptitiously, just like everything that Apple happens. I can just appear out of a cloud of Steve Jobs inspired smoke. And FreeBSD and Linux and Oracle's working on the port for their Linux. So tonight, I'm going to continue giving a little bit of an overview on DTrace, go through some simple examples to set some context. My colleague Dan Kimmel, my colleague at Delphos, is going to talk about a monitoring framework that he's working on at Delphos. It uses MongoDB to collect information about DTrace. Max is going to talk about, Max is from Joint, who's going to talk about debugging of DTrace, and Murray Gray is going to talk and tell you all about all other things DTrace that we didn't have to touch on. But in particular, solving problems, and he knows, I would say, more than anyone in this room, and perhaps more than anyone in the world, how to solve problems. All right, with that, I'm going to stop the slides. Make this bigger so people in the back say they can read it. People in the back, give me a thumbs up. Great, I got a hand from the back. So I'm going to log into as root on my Mac. This is a Mac. The Mac board happened in like 2008, 2009. And it's since been updated, and it's absolutely perfect. It's great to have some insight to what's going on the box pages every day. The same pattern that I'm used to having on the servers that I interact with. So first, DTrace is a Unix command. So you go to the command shell and type DTrace, and like any good Unix command, it prints out a completely indecipherable help message. There is a book and a manual, but we felt like we have to still have that indecipherable help message. Well, the first thing I'm going to do is use this -L flag for DTrace. So DTrace -L lists out all the routes in the system. Oh, okay. So that was my Mac. And just to count, we have about 226,000 probes. So that's 226 distinct points of instrumentation on the system. Different places where I can effectively create a programmable sensor to collect whatever information I need from the scan. Obviously, 226,000 places is a lot to educate yourself about, but there are many that have very high-level semantic information. We'll go through some of those. So the first thing I'll do is do DTrace -N to specify some probes, and then I'll specify the system call probes. DTrace probes are identified by a floor sequence of provider, module, function, and name. The provider refers to a specific instrumentation implementation. So there's one for system calls, there's one for userland probes in your C program, another for userland probes in your Java program. There's ones for kernel function calls, for IO calls, and so forth. And we'll go through a couple of these, and Brendan will go through many, many more. So if I run this, we get a list of all of those system call probes in the system. Now, some of these are towards the bottom more esoteric. If we go up here, we can see, for example, the rename system call, or the demonstrator, the action model system call. I don't know why this system call had before this one, but I can't drop it. And that's select, and all so forth. So that is listing the probes on the system that we're not actually enabling. So I can do it this way. So I would delete myself. We'll change this from a fully optimized Mac system that could be Linux or FreeBSD or Solaris or Windows or SmartOS or whatever. Change this from a fully optimized system to one that has been instrumented in a number of places. So I do this, we enable 440 probes. Now every time a system call is executed in any system by any process, we get that little default action that says, I am here, this is happening. Now this output is damn near useless. But we can record information that tells us about where this is happening. So I can trace, say, executive. That's going to give you the name of the executable that's responsible. Now, unfortunately, we're going to see a lot of DTrace, terminal, and before us also NDS and NTPD, notifying, some crazy things I know about. But this isn't really what the question I'm asking. One of the fundamental building blocks of DTrace is something called aggregations, and it's to give concise answers to arbitrary questions. So what we're going to do now is, rather than tracing out each little IAM here statement, now some of you are probably saying, great, I picked that Perl, I accumulated it, whatever. But DTrace actually has accumulation built into the first-class primitive to minimize the amount of output and minimize the amount of data collected. We're going to do that now. An aggregation is defined by its maximum. I can specify an arbitrary tuple of keys, in this case just one, and I can take an aggregating action. So what this says is every time I get a system call probe, I want to create a little table indexed by the name of the executable, where I just count how many system calls we've done. And all of that. This time I don't see any output because DTrace is kind of accumulated that table internally. Maybe I'll execute a little lower on this system. Start iTunes and hope that was listening to anything really embarrassing. And I hit control state. Now this is more like, this is actually kind of what we're looking for. Folks in the back, can you still see this? Maybe one okay, great. So what we see here are various system calls these different programs have made in about 2 minutes while I was modeling. You see, I love demo DTrace because I always see some weird crazy topology that I have no idea what's going on. They don't know what MDS is. I don't know. So, pardon? Metadata service. Does anyone know what that is? Okay. Let's find out. So, what we do is we limit our focus of what's going on using DTrace just to those specific things. So, I'm going to say, I'm still going to look at all system calls, but now I'm going to use a predicate. Awk, any love of awk? A couple of awk lovers. So awk lovers, love this. So you say exact name equals NDS, kind of an awkish syntax. This is a predicate which limits the scope. So if this is true, then execute the body of this code. And here, now we know what the executable name is, so I'm going to use probe func. Again, the DTrace tuple is defining the provider, the module, function, and the name. In this case, probe func is a variable in DTrace that corresponds to the name of the system call that's being executed. We're going to run this guy, and I hope whatever that data service was doing at the time is still doing now. I hit Control C. Not doing very much of it. This is very scientific here. Quit iTunes. Restart iTunes. Oh, there we go. That was great. So now we see all these system calls that the MDS service was doing. Now, I don't really know much about the MDS service, but I can still kind of peel down into what's going on there. And I'm always interested in nmap. That's one of the unusual processes requesting for some memory to be allocated, and I'm going to dive down into that. Now, I just want to back up and say, well, this is fairly low-level stuff. All of this information applies kind of higher up the stack, whether it's your Java program or your Perl program or your Bash script or whatever. DTrace can provide you insight into all of those and how they interact. So here I'm going to grab the nmap system call, and rather than trace the probe func, I'm going to do ustack, which is the name, or which is the user name stack trace. So now every time the MDS program invokes the nmap system call, I'm going to see where we are. And again, scientist, delete that, start it back up, and hit Control C. So now what I've gone from, I've gone to the specific function in this MDS program that is calling that nmap system call to occur. And it's occurring about 150 times within this program. Now, I'm not an MDS developer, so this isn't particularly insightful for me. But if this is my application, I'm going to drive these to the specific line of code that's relevant for us. we can trace any instruction and any function in any web processing system. In this case, I'm going to look at PIN 62, which in this case is the MDS program that we've been looking at. And then the C is going to be called out. So again, MDS is a program that hasn't been compiled in any funny way, but we can still see anytime it calls any function. Any C programmers in general in here? Several. How many times have you said, gosh, how many times is it calling that function? I know how to do it. We open up Vim or Emacs or whatever, and add a printf, we compile the program, run it again, and it starts spewing out that. But we've all done it. We've all done it. You don't have to be embarrassed, but there is a better one. And DTrace is a better one. So with now any function in your program, you can not just say, I am here, we'll record arbitrary variables in the state of the program at that time. Now that one's one of my favorites because I know variables to it, and I can kind of guess what's going on. But we're going to use a different aggregating action. In this case, we don't need the name of, we don't need a tuple that we key off on it. Instead, we're going to use this quantize aggregating action. And we'll have load generator again. So what quantize does is it prints out a power of 2 histogram of all of the values that are given to it. In this case, I'm giving it R0, which is the first argument to malloc, which is the number of bytes being allocated. And I hit Control C. When we get that histogram, we get that distribution of the size of allocations that program is making, that the MDS program. You can see mostly around 32 bytes, a bunch around 2K, some 8K, some up at 65K. So we have a program that hasn't been compiled in any special way, the one that I can investigate deeply. Let's see, what else? We can look at great. So I have a script playing around in our time because this is not my first rodeo. So DTrace has probes now associated with any function in your C process, any function in your process in whatever language, every function in the kernel, but also functions that kind of make sense, or probes that make sense around I/O. So I/O start, I/O done. The way this script works, move back if I may. Everything I've done so far has been command line. They've been simple liners, but as DTrace scripts become a little more unwieldy, you can embed them into a key script. So they start like bash script, like user s, DTrace minus s to specify the unit in the script. Now what this script does is it says, every time I start an I/O, record a timestamp. Every time that I/O ends, I want to compare that timestamp with the current timestamp I recorded, and display a histogram of how long I/Os are taking. So we're going to run that right now. And we're going to run some new load there to go like this. And we'll find some data I don't use often. Hopefully. All right. So now in microseconds, this is printed out, the latency of these various I/Os. Anyone want to guess why it's so fast? These are all microseconds. So we're peak around 64 microseconds. The slowest of my reads is around 2 milliseconds. Come on, yes, I have an SSD in here, so I'm kind of getting this one. But you can see the distribution of all these different I/Os. And even with an SSD, there are some I/Os that are taking down around 8 milliseconds and over 80 milliseconds. All these writes are super fast, except for some of them, which kind of make it a little longer. So, again, quantize, timestamps, incredibly powerful performance tools. So I talked about during the performance session. All these guys are going to talk about quantizing performance a bit more. Hopefully this gives you a feel for the things that you can do with DTrace, but also going to get into a lot more detail in the next hour or so. Before I get off the stage, any questions about DTrace that I can answer that you're worried that these guys might not be? All right, terrific. Doing well? So thank you very much.